Okay, let's talk about conservative vector fields. The name conservative here, it comes from the conservation of energy from physics, and we will talk about that in the last lecture of this section. For now, let's just talk about what it means and how to test for it. So what it means is that if you have a vector field, it's just the gradient of some function. So that is, you can write it as fx, fy, fz, or just fx, fy if we're in 2 dimensions. And of course, I'm using the lazy notation. Fx is the partial derivative with respect to x. So it turns out this is a very important type and very convenient type of vector field. But let's just talk about how do you test to see if an arbitrary vector field is conservative. And what you actually do is you use the symmetry of the derivatives. So there's the symmetry fx with respect to y, it's also equal to fy with respect to x. And both of these are just equal to fxy, right? I mean, this is just saying that if you have the example f of xy equal x times y, this is just saying that fx equals y, fy equals x. And so if you differentiate fx, you get 1, and if you differentiate fy, you get 1. So these two things are just equal. This is actually called Clairaut's theorem, but I think this is kind of an obvious observation, um, at least in this era, at least in this era. So the reason I'm mentioning this is that if we look at our vector field F and it has components P and Q, we're in 2D, of course, then I'm going to plug in P here and Q here, and this says that Py equals Qx. Right, so this is just saying if P equals Fx and Q equals Fy, so it's conservative, then Py equals Qx. So it turns out the reverse is true. If Py equals Qx, then P equals Fx and Q equals Fy for some F. And you actually need the domain. Should have no holes. But this is not important for this discussion. So the point is, if we can satisfy this condition on F, then we know that F is conservative, and you can in theory find some little f, and this is called the potential function. And again, a lot of this nomenclature just comes from physics. So let's do a simple example of this. This is a very easy one to see. So if we're given this vector field f of x in the first component and g of y in the second component, remember this just means f of x times I plus g of y times j, then the claim is that this thing is conservative. And if we do our test, Py equals Qx, well, we see that P is F, Q is G, so actually Py is 0, and Qx is also 0. So this works. So that means this is equal to gradient F for some F. Okay? And it's actually really easy to see what this is. It's just F equals the integral of f of x dx plus the integral of g of y dy. Right? Because fx is just f, and fy is just g of y. And of course, I mean different things by these f's, right? One f depends on two variables, another f is just f of x. The point is, This is a pretty nice class of examples because, for example, if you see x squared and y squared here, you know this integrates to the gradient of 1/3 x cubed plus 1/3 y cubed. So this would be an equivalent expression for our f. As another example, which is a little less obvious, let's just take a linear function for our force. So you might see this if you're studying the harmonic oscillator. So is f conservative? Well, to do this, of course, we label this p, we label this q, and we do our usual test. If p were fx and if q were fy, then px would equal qy. I'm sorry, py would equal qx. Okay, so let's do the computation. The first term is 0, so we just get -6. And for the second term, we just get -6. So that works for that. So now we need to find f. Because we know now that this is the gradient of some function f of x, y. So now we just need to find this thing. So here's the strategy. So first you integrate fx equals p, and then you plug in to fy equals q. So integrate and solve. So let me just explain what I mean. So you have 2x minus 6y, so I'm going to integrate now. So that's f of xy. We deduce after integration, it's 2x squared over 2 minus 6xy, and now plus that c, so I'm going to call this c, we'll call this g of y. Remember, this is now the constant of integration. In x, and now we plug back in. So the left-hand side, fy will now be 0 minus 6x plus g prime of y. And the right-hand side is q, which we know as minus 6x plus 6y minus 7. So these two things are equal, and we can cancel some terms. All the x's should go away. Which is good because we want g of y. So these terms are equal. G prime of y is 6y minus 7. So g is 3y squared minus 7y plus a constant of integration. And I'm going to call that 0 because we just need 1 f of xy. Not all of them. So we conclude that f is x squared minus 6xy plus g. So it's x squared minus 6xy plus 3y squared minus 7y. Okay? So we conclude that our vector field is the gradient of that thing, that polynomial. Okay, let's do one more example. Actually, this is a non-example. So when there's no gradient. So in the case that our vector field is 3x squared minus 4y squared, 8xy plus 2, turns out there's no gradient. And the problem is there's this minus sign and there's a plus sign here. Now, if that were switched, it would work. So let's confirm this. Let's call this P. Let's call this Q. Then, if this were fx and if this were fy, then py should equal qx. So let's differentiate. We have minus 8y on the left-hand side. For the right-hand side, we have 8y. These are not equal, so this is impossible. So f equals gradient f is an impossible statement. So you can also notice that the 3x squared and the 2, they did nothing, right? That's because these two actually, they arise from a gradient. This arises from the gradient of x cubed, and that arises from the gradient of y. It was just these terms here that mattered. Okay, so I hope this was helpful. Thanks for watching.